I'm going to go through some technology which I've been working on for the last 3+ years. It's some ideas which, it's really history repeating itself. I started programming back in the 70s, assembler, and then got into C, C++ in the 80s. Obviously I was at school at the time. And in those days, we had machines with very, very little memory, and every little tiny bit of memory you had to use, and you had to use it very, very efficiently. Anybody remember the BBC micros? Sinclair, ZX80s, 81s, all those sort of things. They had ridiculously small, well, in today's standards, ridiculously small amounts of memory. So you literally had to use, for example, the screen buffers. You'd have double buffering, and if you needed to do some computation, you'd often use the screen buffers for these things. And if you wanted to run a game, or you wanted to have something, do some computation, you had to use literally everything. So what I did was, working in financial services, started to go and see a lot of clients, and these clients were putting hundreds of millions of messages, and in many cases billions of messages, and they're busy using Hadoop, and they're spending a lot of money to do this. They're spending a huge amount of resources, not just people, but equipment as well, and I thought this is a little strange, because you look at Moore's law. Moore's law is just identifies what's happening. It's not the actual sort of reason why it's happening, but these machines are getting faster and faster and faster. We're getting more and more RAM, and I'm just thinking, okay, the data's not increasing that much. It is increasing a lot, but something's wrong with this. Anyway, so we got into looking at the way we can improve this. So ironically, this beginning of this week started off a little strange for me, because I've been working at a company which I founded or co-founded with some colleagues in 2000. We sold it in 2007. We bought it back in 2011, and at the beginning of this week, that's Monday, sold it again. Interestingly, this company now has the technology which we developed over this. So it's they bought other things as well, but it's sort of proof in the pudding that it actually works. So let me give you a little bit of background. Why do we distribute? As we get larger and larger, we need more and more computational power, we need to start to use other CPUs. Any of these machines we can buy some really powerful machines today. We can buy machines with 48 cores. We can have multiple CPUs in the box, and you get these things which would run entire industries just a decade ago, in fact. But you get to the stage where you need more CPU power, and to do that, you've got to distribute and share the load. And to do that, you've got to go across a piece of wire. We often need memory as well. Why do we use memory? Well, it's a lot faster than disk. Disk is very cheap, but it's incredibly slow. And the next slide, I'm going to sort of point out just how slow that is. So some of these numbers, I'd like you to try and remember these, not the actual numbers, but the ratios between them. Now the reasons, this is something you can just grab off the internet, it's fairly well known. I've redone this side. They used a different ratio. Now the ratio of these, this is to sort of put, for people that don't or can't comprehend nanoseconds, picoseconds, microseconds, etc., this is to put it into sort of real life numbers that we can sort of understand. The way I worked this out was a round trip, San Francisco to New York, it's about 6 hours one way, 5 hours back, etc., and on an aeroplane. So I've basically sort of put it down into aeroplane standards. The difference between the speed of light and an aeroplane is about 1 million times. So these are about 1 million times slower than these. So let's look at this. If we're writing data to disk, we're in the millisecond realm. It takes a long time for the disk, if it's obviously constantly spinning, but the head has to seek to the position where your data is. That's extremely time consuming. Now you'll have multiple heads, multiple platters on the disk, etc., but it's very, very time consuming. You can obviously speed this up somewhat with different levels of RAID. Then we get to SSD, and we're getting a lot faster. There's no physical movement of the disk. And we're down to sort of millisecond, microsecond times. When we get into RAM, and this is the reason why something that doesn't write out to SSD or to disk is so much faster. So we can see there's quite a big improvement here, but look at the difference between the memory here and the L3, L2 cache. That is the cache that is in your CPU. Now that cache is actually quite large. For the average, even a laptop, for the L3 cache, which is the one shared by all of the cores, it's about 16 megabytes. 24, 32, you can get larger. These L2 caches, they get smaller. This is shared by just each core. We're down into sort of 500K. But there's a lot you can get into 500K. That's still typically 10 times larger than the BBC microcomputers that we were using just 30 years ago. So there's a lot of leeway in this. The problem that we have with this distributed technology is not the serialization that's actually putting it on the wire. It's the process of taking it off the wire. It's the process of decoding it. Any data that we send to a computer, that we send for processing, whether it comes from another computer, whether it comes from a human, or whether it's come across the internet, needs to be understood by the CPU. It cannot be processed properly unless it's understood by the CPU. Otherwise, it's just a document or a random pile of bytes. So this, the big issue here is deserialization. Let me show you what this looks like. This is just this is the post-mortem using this rather clever tool that I use a lot from JClarity, of a very simple program that's generating comma-delimited files or comma-delimited lines. So it generates, as you can see, 5 million of them here. It generates them, writes them to memory or to disk, and then reads them back. So the time to generate them is here, the time to write them out is here, and the rest of this is the time to read them back. Why? Well, because the way that they're stored, the way that they're serialized, whether you serialize them to memory, to network, or to disk, is not correct or not understandable by the CPU. So as they're read back, they need to be put into a form that can be used or it can be useful. If we look back at this, who's programmed in C or C++ before? There's quite a lot of you. So you'll remember the days of, if you're trying to make something efficient, you use bit fields, you can use all, you got used to doing this. The whole point of Java was to abstract us from the different size of integers, the different big Indians, little Indians, and you get this language all of a sudden, which is, the actual language is standardized, it's not the hardware, and depending on the hardware, it then dictated the size of the integers and things you'd get. That made it very difficult to have portable C and C++. If we were to take three letters, we want to store A, B, C, and moving into the financial services worlds, ABC would obviously represent, in this case, not a currency, but it's GBP, USD, EUR. We want to store this, or serialize it, or read it back. If you're doing this in most low-level languages, you just need 4 bytes to do this. We have two choices. We can either stick the 0 at the end. This means that this ABC has ended. Or we could put a number at the beginning here which says 3 characters. Now, if you know it's always 3 characters because it's a currency, you could actually say, fine, I will just reserve 3 bytes, and we can make this far more efficient. We just have 3 bytes, knowing that it will always be 3 bytes, and when I write it, it will always fit in the same space. So if I've got 3 currencies, it will be 9 bytes. Nice and easy. When we put this in Java, we have this many bytes or bits, 48 minimum. So every single currency that we store takes 48 bytes. Now we can take a copy of one of those and make a reference, and it will be smaller, it'll be 16 bytes. But remembering that the data is coming off a piece of wire, off a feed, or we've deserialized it, even if you get the same currency twice, you get GBP twice, it doesn't compare it and say, oh, this is the same as the previous one I had. It just reads it in. So each one has 48 bytes. And this is what we get. And it's not just with strings. It's with pretty much any Java object. Some are more efficient, some are less efficient. But every single Java object that you read and write into these things is going to take at least 48 bytes. We could optimize this. We could say, okay, we could put, we only need a byte to store the year, the month, the day. We could optimize it, we get a little bit less, and we could probably get this down to about 16 bytes. But 16 bytes when we only need 3 seems quite a lot. Remembering now, if we were reading this off the wire, the difference between reading 16 and 3, or 16 to 3 to 48, is already quite significant, so we would make some improvements. However, if you take, let's just take a date, and I'll come back to the currency, but if you take a date, this represents, it's not the real stuff, this represents the amount of bits you would need to store a date in Java. If you actually think of, you all obviously, if you've been programming in C, C++, and even Java, you'll know the epoch date, 1st of January 2070, and everything is counted from there. If we take that date, and it's very easy to get hold of that date, divide it by the number of seconds in the day, we can get the number of days since 1st of January 2070. That number is less than 65,000, which means we can store it in just 2 bytes, which means we can store any date between now and about 2160 something or other as 2 bytes. So we need just 2 bytes like this as opposed to 48 bytes like this. If that data is now stored on the CPU as 2 bytes, we can do date comparisons. We can say get everything greater than this date, less than this date, equal to this date, and we can now start to do analytics, and it's in the right format. Imagine now when we serialize this, instead of serializing, and when we do Java serialization, we don't just serialize this, we serialize the name of the class as well. So we get java.util.date and the content of this. So the actual serialization of a date is actually about 80 bytes. It's quite significantly larger. Rather than this, if we know we're serializing a date, and we serialize just 2 bytes, when we read it back in, it's going to be vastly more efficient because we can already use this. It's in a CPU-efficient format. So extend this a little bit further. We take something, comma delimited file. This is the one that I used in the example. We've got dates. So we could now move that down to 2 bytes. By cell, anyone want to guess how many bytes we need for that? Come on, it's not that early in the morning. 1 bit. Yep. So we need 1 bit. Bits are inefficient, so we'll use a byte for this. Bits we can use. If we had lots of them, we could use lots of bits, and eventually we'd make a byte. But yes, a bit is all we need. Typically, we'd use a byte for this. Currencies. Now, we said 3 characters, so we'd need minimum 3 characters. But if you actually look at the ISO currency table, there are only, in fact, 163 currencies defined. So 163 currencies less than 256. Therefore, we only need 1 byte to store every single currency. What if we want flexibility? What if we want to put precious metals in there? We have XAU for gold, XPT for platinum. Okay, we can add a few more in there, but there's not that many precious metals that are traded. We could also add an escape sequence. So we could put an escape sequence. So if it's 0 or 255, we could say that the next 3 bytes are the currency. So we have plenty of flexibility in this. Numbers, IEEE standard's already pretty efficient, so we're not too far off with this. We do need some flexibility. We need to make sure we don't get rounding, so we're probably down to 4 bytes for these. Same with exchange rates. We can store, exchange rates are only 5 significant digits, therefore we just need 2 parts, the 5 significant digits and the multiplier 10 to the power of. Back to the currencies, back to the numbers, and back to the dates again. So we can store this very, very much more efficiently. This comes in this format. It's roughly, on average, about 70 bytes per line. This is using ASCII. Naturally, if it's UU encoded, it's twice the size. But let's stick to ASCII for the moment. When this comes in, it's not in a CPU-readable format, so it has to be parsed. This character here, the 2, is ASCII code, or ASCII character 32. The next one is 36, 30, 34, 35, 33, etc. So those have to be computed, multiplied by 10 or divided by 10 as they come in, so that we actually take this number, which is in binary encoded decimal. In fact, no, it's not even binary encoded decimal. It's actually in ASCII, and we have to read that in, and that's the thing that is taking the time to parse this file. So if I ask someone any one of you, or anyone else in an interview question to code up a class for this, this would not be something that you would fail the interview for. It's for the data that we've got up here that we can see. This looks reasonably good. Possibly fail them in an interview if they put an int in here, because it's very easy to wrap around the ints. In some of the telco stuff that we've done, we've actually wrapped around the longs as well. We found after a couple of days the longs have wrapped around because the amount of data we're getting in millions per second. Anyway, trade dates, strings, but think how much space this is now taking, not just in memory, but think of the serialization. So we got, obviously, 8 for this, and the way that Java stores it. We've got 48, 48, 48, 48, etc., all the way going down. When we serialize this, it's even worse. And I'll come to that very shortly. So we write this class, we write getters and setters, and with the getters and setters, we could do something as simple as parse the line. We use a line split, so we just say line split on the commas. It's not doing anything particularly fancy. And we just simply use the getters and setters in here to say, set trade date, we get the format, we get each of the fields, 1, 2, 3, 4, 5, etc., and everything works. It's nice. It's pretty quick. We could parse, as you've seen, several million lines fairly quickly. And that's classic Java. The problem is when we start to scale this, and this is the problem that we've had since Java came out in the mid-90s. We weren't globalized in the mid-90s because although the internet did technically exist, no one was using it. We didn't see the internet coming in and messaging taking over from databases. We were in a database-centric world in the 90s. As the internet's come in, we've now got a message-centric world. And it's quite normal to expect to get messages coming in from everywhere on the planet. And all of a sudden, the scale that we need has ballooned out. And our simple Java now starts to show performance problems. So this becomes very, very verbose. Who here thinks that XML is a sort of a verbose standard for data? Yeah, quite a few of you. Well, I can tell you Java is worse. Java is actually worse than XML. So if you're putting your data from Java into XML, you're actually saving space, believe it or not. This 70 lines, roughly 70 per line, comes out at 328 bytes in memory. That's a lot. So reading in a million of these is not 70 megabytes. We now need 328 megabytes. This is half a gigabyte just to read in a million of these. And that's assuming you haven't got any inefficiencies in the way that you've stored this. So we've already bloated it about 4 times larger. And that also has to be read from the disk or read from the network. That's bad to start with, but we haven't got into serialization yet. So Java is really bloating things. I like to think of it like this. For those of you that program in C, C++, everything, if you want to process vegetables, it's all beautiful, crisp, really nice and fresh. When we're working in C++, it's pretty hard to get everything right and the memory right. And yes, this all could get crushed and distorted if you abuse your memory. But when we work in Java, we work in a much more protected world. Every one of those things is wrapped up. It's wrapped up with garbage that we don't need. Those 2 bytes that we actually needed for the date, yes, I've stripped off the hours, minutes, seconds, and milliseconds, but we could add those with another few bytes. This isn't even correct. In Java, each one of these would be individually wrapped inside the container. So we'd have individually wrapped things inside wrapped things, which would be inside more plastic bags. And that's what we get. And that is another problem. So we've got 2 problems now. One is that the data is inefficient, and we're not using it correctly. So the CPU is working overtime, seriously amount of overtime. But we've also now got to go back and collect all of the crap that we've left as we've processed this. So everything that gets left around this needs to be cleared up. It's not just Java. For anyone that thinks, I'm using the latest wonderful language that makes Java look silly, I'm really trendy, so I'm using one of these things. Actually, some of them are pretty good. Kotlin's great. But it's the same problem. You're working in a JVM, and if you think, okay, I mean, I doubt many people who works in Microsoft here or with Microsoft languages. Okay, a few of you. I mean, you have the same problem. You're working inside a virtual machine. The virtual machine is abstracting you from the hardware. You're getting the same issues with this. If you're putting things into memory, rather than using a map or something that comes with the language, you're probably often using one of these in-memory data grids. This, I wouldn't say solves, but it makes your life easier with distributing the data. So if you're putting data into these, you can write into Gemfire, Coherence, Neo4j, Hazelcast, etc. You can write it in, it will distribute them for you, but what you're not seeing is all of the stuff that goes on underneath, and all of the serialization. Now, some of these have optimizations for this, but it's still a lot of work that needs to be done. So how can we solve this? Let's go back, look at the Java work. If we were taking this classic and we were putting it into standard Java code, we could generate this, and this is Java binding. Those of you that have used, anyone used JAX-B, JIBEX, these sort of things? So you've got perhaps a database, you've got XML, and it will generate the Java code for you. That's relatively simple and easy to do, but what it's doing is generating this from this. And we just said it's acceptable, it's okay, but it's starting to use a lot of memory. So what happens if we just store the row? Well, all of a sudden, we've now improved the size of the memory from 324 down to just 70 bytes. So we've made a huge improvement. But now I've got 1 billion of these rows. They're much smaller, which is great. How do I search through them? If I want to search through these, I've now got to go back and parse the damn things. So when I'm reading this line, I want to say get everything which is above a particular date, which has a buy with euro against dollar. I have to parse every line, and every line that I've parsed, I then have to parse the data in it to understand it. I could build an index, but I'm storing objects in the index, so it makes a complete farce of having to store it in this way. So it's very good for storage, but it's not any use for actually processing the data. So the CPU needs to understand what's in there. So original data would go in. This is quite useful for XML because you've got to parse out all the XML. If you take a standard XML contract like FPML in the banking world, it's up to about 25K just for every single contract, and you could have hundreds of millions of these things. So it uses up a lot of memory. There are banks around here in the city which have tens of terabytes of in-memory storage, and that's a lot. It's expensive. What about compression or compaction? Okay, what's the difference? Well, if we were to compress them, we have two ways, as anyone that's tried to compress a file, there's two different ways you can do it. You can either compress individual files, and you get a relatively okay compression ratio, but if you compress everything together, you get a much better compression ratio. Okay, so now we've got 1 million of these rows. If we compress them, that's pretty good, but if we want just one of them, we have to decompress the entire 1 million of them. That's not so good. And not only that, but it generates and needs a lot of memory to do that. So now we compress individual lines instead. Well, hang on, that also takes a long time. Not only that, but I've got to decompress it before I can even understand the content of it. So that makes it even slower. We've saved even more memory, but it makes it even slower. If we compact it, let's go back to the Java date. So if we compact it, we've now only got 2 bytes, and we don't need to decode the entire message to be able to read those 2 bytes. We just need to know where they are. So all we need to do is calculate where those 2 bytes are that we need. We can read them into the CPU, and we can immediately do the comparison. So move this into binary. If we store every one of these rows simply as a byte array, and that byte array is not the ASCII that was in this, but the binary that we have replaced this with. So we have maybe 4 bytes at the beginning for this, or 8, depending on what we want to keep it as. We have 2 bytes for the date. There is no time in there, so it's just we need 2 bytes for that. We have 1 byte for the buy-sell. We have 1 byte for the currency. That's all we need, etc. as we go across. We can get this down much smaller. You say, well, now we've got to change all the code. Well, you're working in an object-oriented world. We have encapsulation. So if we have get trade dates and set trade date, which is the typical way we would do with the class, if we replace that with get trade date, and I'm just using the simple example here, so this is getting the date from the data. So we go and find, this is just something that goes off and finds the date in this particular case. This could be complicated if it was something larger. It could be simple if it's a fixed length format. So in this particular case, it's at offset 8, and we read the word back. Now, we don't have words in Java, so we read this back into a long. The rest of it is zeros or whatever you want it to be. And Java has this rather convenient ability to actually take a long, which is the number of milliseconds since 1st of January 2070. What we do is multiply this number by 86,400,000, which is the number of milliseconds in the day. If we do that, we pass in a new date, we get back the original date. So we can go from 2 bytes to a full-size date. Why? Now, we just said we really want to avoid objects because we want to avoid garbage. So what have we done here? Well, we've used this word new. New creates another object. So every single time we'll be calling this method, we will be getting a new object. Surely that's not good. Well, Java, the way the allocation works is divided, the JVM is divided up into separate sections. These, if they're used very quickly, because we get the date and we use it as a comparison, for example, as soon as it's been used, it's garbage collected. It's from the Eden space. So this is like if you like, a ring buffer. It's incredibly fast. We tried to do some clever things with this by using static fields on this so that they'd be reused. And we went to talk to the guys at Oracle about it, and they said, just ignore it, just use new. It's actually faster. It will be garbage collected even quicker. We did, and with the, whatever it was, 1.6 version underscore sort of 70 something or other onwards, it worked incredibly fast. This is effectively, it's free. It's almost free. It's comes down to sort of single instructions. Same with the trade date. We take the date, we get the long, we divide it by the same number, and then we use these things that C++ programmers will remember very, very well. We use them all the time, or C programmers. These are rotate, right. We have rotate, shift, etc. Now, I don't have time, unfortunately, to show you the code, but if anyone's interested, I've got the code. You can, if you've got a memory stick, you can walk away with it, or give me an email and I'll send it to you. It's just a simple example of how this works. And in this, I've got 2 comparisons. I've got the same piece of code. Because we're using effectively like an interface, we're using the getters and setters, I can run it with both classic Java objects and I can run it with binary objects. Looking at the results, I mean, all I do is run it as the demo. So looking at the results, this is the amount of bytes used in the classic Java object. This is what we use with the binary version. I could compact that down a little bit further as well, because I used an entire byte for the by cell. When we serialize it, as I said, the serialization is the name of the class and then the content of the class. It's tag value pairs as we serialize. But if we serialize one object that contains multiple other objects, you get name, content, and then inside that you get name, content, name, content, name, content. So each row started off at 70 bytes, now serialized is nearly 700 bytes. 10 times bigger. That's why Java is slow. Not only that, but it has to read it back and still decode it. The binary version is 85. Now, it's gone up because it's actually the class name that I used, something like binary demo or something like that. So I've got john.davies.binary-demo or something, and that's where these extra bytes have gone. Now, we can now, because in a Java object, if you wanted to store a string, you don't know where the memory is for the string. That's the whole point of the encapsulation. You have a pointer or a reference for the string. You can get the data from the string, and you can actually take it out and you can write it. That would be customized serialization, so we could avoid it. But when we've got a byte array, we know exactly where the memory is, because we can basically iterate through this byte array. So we can now use custom serialization, because we know it's 39 bytes in size. In this particular case, not in every case, it doesn't vary. So let's just round it up to an 8-byte boundary, and we get magically 40. This means we can now write, if we've got 1 million of these, we can write out an array of 1 million times 40. So 40 megabytes for 1 million of these things in one go. Interesting advantage now, we can seek to any one of those, and we can read out the data almost instantly. Not only that, but when we read it back in, we can actually, if we know we're reading in 1 million, we can read in 1 million rows as using Java NIO in one go, directly from the disk, directly back into memory. Not only that, but it's immediately understandable. There's no parsing to be done. Now look at the performance now. So we take this standard serialization, 41 microseconds typically, so we're getting, 250, what is it, about 2.5 million, 2.5 thousand a second on this. When we use the batched, i.e. writing out 1,000 or writing out 1 million of these as binary, we're now down to 44 nanoseconds. So we've got almost 1,000 times increase in performance. And that's typically what we do find out of this. Let me just show you some comparisons. These two graphs, I will enlarge the one on the right in a second. This is the post-mortem heap usage of the ordinary Java object version. This is 200 seconds, so 200 seconds down here. This is 8 gigabytes of heap. This is creating 5 million, writing them out, and then reading the same 5 million back into a second array, so we end up with 10 million in memory, hence the increase in size. So 8 gigabyte heap. This one is a 2 gigabyte heap, and this is 40 seconds. And I just sort of scaled them so you can see them roughly side by side. What's happening here is exactly the same as what's happening here. The fact that the slope looks different is just because the scale is different. So this part here and here is the same. This is the reading it back. So this is the deserialization. So the deserialization, we're writing them out. Creating, serialization, deserialization. And as you can see, just on this very simple example, 5 times faster. Look now at the heap usage. So this is the GC pause time. GC pause time is what kills most applications, particularly if you're working in a should we say, real-time or pseudo-real-time or something where a GC pause will kill your machine. One of the best ways of avoiding this is to have as little memory as possible. And you have multiple machines. If you have little memory, then you've got to distribute it, and you're back with the same issues again. If you have a very large amount of memory, you get less GC pauses, but when they happen, they're into the sort of seconds and tens of seconds, and it shuts your machine down. And given the way Java works, it will also, even if you're single-threaded, it will grab every single core on your machine. It will kill your machine, and I'm sure you've seen it occasionally when it goes haywire. It's quite easy to replicate. And sometimes it gets to the stage where it doesn't actually catch its own signal to throw the out-of-memory exception, in which case your machine will just go into a horrible die, and if you're using a laptop, all the fans will come on and it'll start getting pretty hot. And I'm sure you've seen that. So let's just look at this again. 200 seconds here. This is half a second. 2 half-second pauses in this. This is 40 seconds. Now, the very bottom rung here is 50 milliseconds. So you've got 50, 100, 150, 200, etc. Half second here. The top of this one is 45 milliseconds. 45 milliseconds maximum pause time, and 1/5 of the time to actually process it. This is a really, really simple example. This is something that if you've got data that you're using, distributing, and you can make very, very small modifications, this is the sort of performance you can see. When we did this to more complex things like XML, we got performance increases by, in the realms of, in this case it was 5, we got in the realms of 50 times faster, 50 times less memory. And that was very, very significant. So it's the serialization and deserialization which is causing the problems with this. And this is, there are many, many frameworks. In fact, probably 20, 30 different frameworks because serialization is so slow. It needed to be compatible across. So anybody worked with any of these? Avro, Cryo, Thrift, Protobuf, etc. at all? These are significantly better than the JVM because the JVM is just so bad. So you can do pretty much anything and you're going to improve on the JVM. You can write your own serialization, and effectively that's what these do. But these also store tag value pairs. They store a token to say, I'm going to send you a string, I'm going to send you a date, I'm going to send you something else. If you're sending data from A to B, typically you have a contract. B knows what A is sending, so why bother to send all of the details about what you're about to send? If you send XML, so if you go to a REST-based service or something and get JSON or XML, you've typically got a schema that defines what that is. And because of that, it's well defined what's being sent. Now, if you're sending serialized data, or you're storing data in a serialized format, you don't actually need to store the contract or the content of the message with every message, because it's not going to vary. You need to store some tags and some tokens to say this will either be one of these or one of these, and you can put that into a bit or a byte, but you don't need to do the tag value pairs. So when we compare this with these, if we just do straight binary writing out, it is very significantly faster than these as well. Anybody use JMH before? Another one of these things, really highly recommend. If you want to walk away with something sort of useful to use, this is an amazing tool. JMH, just search for the Java micro benchmark harness. Unbelievably useful. Does some really nice stuff, creates all of these very, very quickly. The downside is it uses Maven, which I hate, because I spend so much of my coding time on planes, and of course Maven doesn't work on planes because they haven't got Nexus repositories on them yet. Still waiting for that day. But when you put in this micro benchmark, what you do get out of it is, for example, you can see this is nanoseconds per op. We can see 171 nanoseconds for binary serialization. And with cryo, in this particular example, quite a bit slower. It is still very significantly faster than Java, than standard Java. Benchmarking it across all these different ones, Thrift, Protobuf, etc., we can see we got some pretty good performance here. The other interesting thing is this is serialization, and deserialization is virtually instantaneous because it's NIO. This was an open source benchmark that we used. As realistic as this particular benchmark was, but it did mean that we got pretty much instantaneous readback on this. If we're doing analytics, this is where the CPU comes in. If you're analyzing very large amounts of data and your data is stored in Java objects, every time you use those Java objects and you've got an array of maybe 100, 1,000, 1 million, because you're searching through an array. So you're saying, okay, of my array, I want to get everything which is between these dates and between this amount of currency or between these things, and I want to process it. So I want to do a lambda here with a map reduce where I'm getting the currency amounts so I'm basically doing a map reduce across each type of currency, starting with a big decimal from 0, and I'm getting the amount, and I'm basically adding this up. So I'm basically, for each currency, get me the total of each of the currencies. If it's in Java objects, it's very fast. If it's in these binary objects, I've now got to do a little bit of calculation. So you might think it's actually slightly slower, because I've now, for example, with the dates, I've now got to do this manipulation of multiplying by 86,400,000, for example. You think, okay, it should be slower. What actually happens is, because we now have an array of 1 million of these, or 10,000 or whatever it may be, that array is read into the cache. Because it's in the cache, I'm not doing memory fetches. So I'm going from my 120 nanosecond fetch time from memory, I'm going straight into the cache. Now in Java, I'll get a lot of it in the cache, but when it's stored in binary, I can get even more in the cache. And we actually find that the binary objects are even faster than Java objects, which is sort of weird, because you're actually doing more work, but it's actually faster. So we have the ability, because we've encapsulated it, even though it's stored in binary, we can still do everything that we could do before. We get some very, very high performance and interesting results, but we could do it a lot faster. Anybody use Hadoop here? Maybe? Yeah, don't bother. Anyone use Spark? Yeah, a little bit more intelligent way of doing it. One of the problems with Spark or Hadoop is that as soon as you've gone past the capabilities of the machine you're working on, you've got to distribute. You have two choices. You basically run out of CPU power and memory. You can either go to disk, so you put everything on the disk and use the existing CPU, or you can distribute, and you can go to more memory, which is faster, but you hit serialization, and but you get the extra CPUs. The problem when you do that is, let me just show you here. This is the speed that it takes in standard Spark when we're on the same machine, but as soon as we hit what's this one, cache serialized memory or distributed memory, we hit this cliff. Anytime that you distribute, you hit this massive cliff because we have to serialize it. So Spark comes quite standard as one of the optimizations you can use is cryo. It's the optimized serialization, which means that as you use Spark, it's faster to use the serialization. You can see there's an improvement. Okay, these are benchmarks, so don't necessarily take them as sort of fact or figure. What I would ask you to sort of really notice, even though it's just a benchmark and all benchmarks can lie, there is a massive difference here between these two because we've now improved the serialization because we're reading this stuff directly back in a format that the CPU can use. Using binary, we can now distribute, and we don't have this cliff as we hit the distribution boundary of the network, where basically it's just like a ledge. So really, just to wrap this up, if you can rewrite a little bit of your code, keep encapsulation, you can get some incredibly fast performance out of your data. You also don't need to distribute quite so much because you've got more data in the memory that you had in the first place, quite significantly more. It's incredibly fast, and not just from the benchmarks and the tests, but from actual customers we installed this with, and some very large customers using this. Going from, this is the object, and again, these particular numbers are just benchmarks. Cycling through, I don't know what this was, 100,000 FPML messages. These are very complex XML, but these are binaryized. Java objects took 22 milliseconds, but the binary version only took 17 milliseconds. So we're starting to already see some of the performance gains from hitting the cache. We have more work to do, and the XML was more complicated because you have to work out where the data is. And because you've got recurring elements in the XML, it's much more complicated because you've got things that vary in size, and you're stepping over data to find out where the data is that you want. Despite all of that extra work that had to be done, we still got performance increases over standard objects, and the data was a fraction of the size. Transport friendly. The other advantage, when you run out of memory, you just write it to disk. If you've got something like SSD, because you can write it to disk and read it back into memory with no parsing, that's important. There's no deserialization to be done. You read it directly from disk, directly into memory. You use it instantly. So to write something out to disk is only a sort of 50% slower than actually using it in memory. So a typical machine with, let's say, 16 gigabytes of RAM and a terabyte plus of disk, you can actually use that terabyte almost as if it was RAM. It's slower, naturally, but almost at the same similar performance, which is just absolutely impossible using standard Java objects. So hopefully this is the last slide. What I'd like you to walk away with here is a little bit of, there's a lot of things you can do to improve the code that you've got, to improve performance, to make small changes, to make small tweaks. But this is something that I've taken, stuff that we used to do 20 years ago was just standard practice. This is something that you can go back, and I've done this with many initial clients where we go in, we look at the data they've got, and within half a day, you can start to see some incredible performance increases by taking the objects that you've got, making a couple of small modifications. From half a day, you can go to a week. You can say, okay, we've seen some performance improvements. We'd go to a client, for example, that had massive amounts of data. We'd take it away from the evening, rewrite the class, put a few little improvements in there. They would see a 5 times performance gain, 5 times less memory, and all of a sudden, in the space of one day, that gave them something they were about to do an entire 6-man-month plus project on, and we've done it in one day. So if there's anything you can walk away with here, this is a very, very small change you can make to your code that makes a massive difference, both to the performance and the way that your CPU uses the memory. I've hopefully got a little bit of time for some questions. Other than that, I'd like to thank you very much. Any questions at all? Yep. C++ program here.
Well, I'm from a Microsoft background, so don't boo.
Never mind.
it sounded to me, unless I misunderstood, that you've kind of ruled out compression as a way to improve performance. But I don't know if you're aware of Microsoft's column store indexes that they use. I'm just wondering whether that would be a good way to get a really, really good compression factor from your data, and also another of their technologies in-memory OLTP, where they use hash functions, so hash buckets.
Yep.
I wondered whether combining those kind of two methodologies would maybe make that a viable, addition to.
Yeah, absolutely. I think the hardest thing we found as we thought, okay, this is going to change the world in the Java world, and then you go to clients and so many of them were using existing optimizations to get around this in similar sorts of ways. A lot of the in-memory data grids already had pre-optimization for certain things, and you're effectively not competing with that because you do complement it, but there's an extra little bit of work we had to do to make that complementing work with the existing optimization. So in answer to your question, yes, it can be used. Because there's optimization and you're adding more optimization, it's sometimes a little harder to get the two to work nicely together. We did manage that in every case. We did manage it. If you're going for something completely unoptimized, this is a superb optimization. If you're going for something already pre-optimized, you have a little bit of extra work to do. But it did make a very, very significant performance improvement. And one of the, I was using Microsoft back in the 90s before Macs and Linux became quite so available, so I've got a long background in the Microsoft world as well. And a lot of the clients use Microsoft as well. Microsoft is not the issue, it's just the fact you have to pay for the licensing, and if you can basically reduce the amount of machines you're using, you reduce the licensing. Another question? I saw a twitchy hand, I thought, and someone just coughing. Any more questions? Okay, thank you very much.